Hello there, so it's evening and we're gonna have a look at MiniGPT-4. So this is the website, so let me squeeze myself into the corner. Here we go. Let me also make this, I have a wide screen, so it's a little bit challenging with recording this way. So transform, let's fit to screen. Okay, so MiniGPT-4 enhancing visual language understanding with advanced large language models. So I say we go immediately to the Gradio demo. So basically this is a language model that you can pass an image and it's able to use the image as an input as well. So I have a couple of memes that I just download. So this is the meme one, basically. When your best friends start telling an embarrassing story about you, please upload and start chat. So let's see. Ah, nice. So 532 seconds. Well, let's say we start. I don't know. We can also have a look at the code here. So let's see a couple of examples. Okay. Okay. The email. The link is broken. So here we have a beautiful image of a windmill. Very nice image. So and it says, "Give me a short story about this image." And the model says, depicts a peaceful countryside scenes with a windmill standing tall in the center of the image. Blah, 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 blah. And then it's saying a short story. A short story based on this image could be about a man who lives in the countryside and is surrounded by the beauty of nature. Blah, blah, blah. Nice. And then we also have some example. Describe this image. The image shows a cattle plant standing in the middle of a frozen. Okay. Yeah, I mean it seems to work well. Uh, so yeah, it's gonna be a little challenging run this. Also because they have nothing here to explain you how to run. But one could just go on the damn, they don't have a code to show to run it. Really? Prompts, I mean examples maybe. Oh yeah, we have demo. Yeah, so we do have code here. Yeah, it's beautiful. Now they sure, not sure I can run this on my 3090 though. I have to say, I'm not sure. Well, we can just go ahead and read the website. And oh, they have alternated demo links. Nice. So let's pick just one. Let's only one. Yeah, let's see. Slightly better. So let's go ahead and pick. Yeah, the fifth one. Yeah, I don't want to spam too much. Let's go ahead, select me one. Let's see if the fifth one is the lucky one. More or less same thing. Yeah, we can just wait. In the meantime, we can just go ahead and read. So, okay, I guess we can go ahead and read the paper, right? There's not too much here. So, paper. They also have the dataset, some dataset. Wonderful. So I really wish they can have some sort of dark mode I'm gonna create a new window capture because I opened the paper, and I'm gonna select the yeah, the paper here. Okay, I need to tune my screen brightness because too much white for night. So yeah, so let's have a look. The abstract. The recent GPT-4 has shown extraordinary multimodal abilities. I still have to try that. I just saw a video on YouTube. I don't know about that. Such as directly generating websites from handwritten text and identifying humorous elements within images. We just saw the video, we don't know that. These features are rarely observed in previous vision language models. We believe the primary reason for GPT-4's advanced multimodal generation capabilities lies in the utilization of more advanced large language model, LLM. To examine this phenomenon, we present MiniGPT-4, which aligns a frozen visual encode with frozen LLM, Vicuna, using just one projection layer. Okay, so this is really interesting. Like, you take a frozen vision model, you take a frozen transformer model, and I guess somehow you want to translate the tokens that come from a frozen transformer vision model to something that a frozen language model can understand, right? This is usually what is referred to a line or alignment. Our funding reveals that MiniGPT-4 possesses many capabilities similar to those exhibited by GPT-4, like detailed image description generation and website creation from handwritten draft. Furthermore, we also observe other emerging capabilities in MiniGPT-4, including writing stories and poems inspired by a given image, providing solutions to problems showing image, and teaching users how to cook based on photos, etc. In our experiments, we found that only performing the pre-training on raw image text pair could produce unnatural language outputs that lack coherency, including repetition and fragment synthesis. So here we are saying, if we only do a pre-training, I guess by pre-training that means that they really pre-train everything on image and text. So you can basically teach a model to understand the text in an image, and that's also a very difficult thing, because be able, to have very good text and image data points, pairs of text and images, it's hard. To address this problem, we curate high quality, well-aligned data set in the second stage to fine-tune our model using conversational template. Don't know what a conversational template is. This step, I guess, you have some sort of images and text and some conversation that is started with that image, I guess. This step proved crucial for augmenting the model's generation reliability and overall usability. Notably, our model is highly computational efficient, as we only train a projection layer utilizing approximately 5 million alignment image text pair. I mean, yeah, cool. I mean, your model is highly computational efficient. Yeah, I mean, the alignment layer is highly computational efficient. Our code, pre-trained models, and collect dataset are available at blah blah blah. In the meantime, I'm gonna see if we were able to. Yeah. We were able to get inside the. Yeah. Why this image is a funny thing? Okay, let's go back to the paper. That's 2 minutes wait. Okay. Well, we skipped the introduction as always. We present a summary of our key findings. Our research reveals that by aligning visual feature with the advanced large language model, Vicuna, we can achieve emerging visual language capability. We demonstrate that our MiniGPT-4 can process abilities similar to those showcased in GPT-4 demonstrations. By utilizing a pre-trained visual encoder and a large language model, MiniGPT-4 achieves greater computational efficiency. Our findings suggest that training manually one projection layer can effectively align the visual information with the large language model. Our MiniGPT-4 only requires training approximately 10 hours on a 4. Oh, this is sweet. That like this is like $4 or $5 per hour on Lambda Labs, so less than $100. That's, yeah, I mean, that's amazing, right? We discovered that simply aligning visual features with large language models, usually using raw image text pair from public dataset, is not sufficient for developing a well-performing MiniGPT-4 models. It may produce a natural language output. So then we will discover what they mean with a natural. That lack coherency, including repetition and fragmented sentences. Addressing this limitation requires training with a high quality, well-aligned data set with significantly improved its usability. Okay. So related work. This is for large language model. Yeah, so basically here they are saying, hey, if you have a large language model and you fine tune with instruction prompts, it's gonna work better. It's gonna be able to follow better human instruction. Love this feature. Okay, so let's see the leveraging pre-trained LLMs in visual language tasks. In recent years, the trend of using auto-regressive language model as decoder in visual language tasks has gathered significant traction. We can see we are the data fish. Yeah, that's the, don't remember. 15 language is not all you need. Perception with language model. I don't know this paper, but that could be a cool read for the future. This approach takes advantage of cross-model transfer, allowing knowledge that can be shared between language and multimodal domains. Pioneering students like Visual GTP and Frozen have demonstrated the benefit of employing pre-trained language model as visual language model decoder. Okay, so you don't need to train it from scratch. You can use one model that is big already there, and you maybe can just go ahead and fine-tuning. Flamingo was then developed to align a pre-trained vision encoder and language model using gated cross-attention. Gated cross-attention, I'm not sure what gated is, but I guess they have a vision encoder, they have a text encoder, and they basically cross-attend to one and another. I guess I scanned through the Flamingo paper some time ago, I don't remember. So I hope that's the correct Pullman explanation. And was trained on billion of image text pairs, showcasing impressive in-context few shot learning capabilities. Follow that, Blip2, I read the paper on my Discord with some other people. I found it very hard to actually follow. Yeah, because they introduced a Q former, to efficiently align visual feature with the language model. Okay, damn, I don't remember what the Q-former was, but that I think was the whole point of Lip2. Most recently, Palmi, featuring 162 billion parameters, has been developed to integrate real-world continuous sensor modalities into a large language model, thereby establish a connection between real-world perception and human language. GPT-4 has also been recently released, showcase more powerful visual understanding and reasoning abilities after pre-training on a vast collection of aligned image text data. Okay. And I want to get into how it works, this is super cool, but I want to get into how it actually works. Okay, so MiniGPT-4 aims to align visual information from a pre-trained visual encoder. In the meantime, I'm checking the demo. The model is typing. To align visual information from a pre-trained visual encoder with an advanced large language model. Specifically, we utilize Vicuna. Vicuna, I think it was Llama fine-tuned on the dump from a website with all the GPT-3 and 4 conversation that was called Share GPT, if I'm not mistaken, as our language encoder, which is constructed upon Llama and can perform a wide range of complex linguistic tasks. For visual and perception, we employ the same visual encoder as used in Blip2, a bit backbone coupled with their portraying Q-former. Both language and visual model are open source. We target to bridge the gap between the visual encoder and language model using a linear processing layer with an overview and our model displaying figure 1. In the meantime, I can see the demo is there, and let's have a look. So, demo. So I asked the model why this image is a funny meme. The image is funny, it's a funny meme because it shows two people fighting with a sword. Which is not a common sign in everyday life. They capture when your best friends start telling an embarrassing story about. Okay, this is amazing. The OCR capabilities adds to the humor of the situation. It's a light-hearted and humorous meme. Okay, so let's ask. So let's do a little bit of self-reflection here. Are you sure it's a sword? Doesn't look like a sword to me. Okay. Nice. So I guess we have a look at figure 1, and then we have a look at, like, the method itself doesn't seems to be so novel. Like, it's taking some components and placing together in a very smart way and be able, to have the knowledge and the know-how to train it. So I think maybe we will have to go a little bit back and look at the Blip2 paper, but let's go on figure 1. Okay. So, frozen language model, VAT Q-former that are able to understand the image, linear layer, and place them inside. So to me, it looks like the linear layer is the only part that, it's the only part that was trained. And then here we have the logo is simple and minimalistic with a pink line drawing. So I guess the pink words are the words refer to the image. The architecture of MiniGPT-4 consists of a visual encoder with a pertain VAT and a keyformer, a single linear projection layer, and an advanced vacuum large language model. MiniGPT-4 only requires training the linear projection layer to align the visual feature with the vicuna. Okay, so I'm kind of wondering, how do you train this? Like, what's the output here? I mean, what's the output that you train upon? Like, you need to have image and text pairs. So it will be very interesting to also have a look at the dataset, which I'm going to download it. It's only 29 megabyte. Oh yeah, so I am downloading the datasets. In the meantime, behind the scenes, going to download it, extract it on my download folders, and okay, and then I'm gonna open the folder with Visual Studio Code. Downloads, CC, and code. Okay. Sweet. Okay. Damn. This is really amazing. Really amazing, guys. Yes. So let's go on the Blip2 paper. So I mean, like, we need to check the Blip2 paper, since apparently I read it. I don't remember it. So I'm going to download the paper in a sec. Yeah, we can try to understand it. I can see the model is writing on the demo. In the meantime, I can see that the model is writing. I'm going to store the Blip2 paper. Yeah. And we will also be able to look at that. Yeah, the model is typing. So, Blip2 paper, and I need to create a new window. Let's go. Okay. Wait. Look at the demo. Look at the demo. Demo. So I say, are you sure it's a sword? Doesn't look like a sword. To me. Typo. Apology for the confusion. This is the thing that GPT-4 says. Upon closer inspection, it appears that the object in the image is not a sword, but rather a stick on a branch. The image, okay. Yeah, it's not really correct. Can you make 10 guesses about what the object is? Man, this is fucking amazing. Really. Okay, the Blip2 paper. Come on. Let's do this. So let's see. So the goal of this model is to do capturing, right? I guess. Let's see. This paper proposed Blip2, a generic and efficient pre-trained strategy that bootstrap vision language pre-trained from off-the-shelf frozen pre-trained image encoder and froze language figure models. Okay, so this is a pre-trained strategy. They also, the goal of this paper is give you a pre-trained strategy that bootstrap vision language pre-training, bootstrap window language off the shelf. Okay, so here we have visual language representation learning. Okay, in which we have these queries, no idea, and the text, image encoder, and then we pass them to a large language model. Okay, they say overview of Blip2's framework. We pre-train a lightweight querying transformer following a two-stage strategy to bring the modality gap. The first stage, bootstrap vision language representation learning from a froze image encoder. The first stage, bootstrap vision language representation learning. Okay, the second stage, bootstrap vision to language generative learning from a frozen. Damn, I kind of confused. The vision stage, bootstrap vision language representation learning. So basically here we are trying to get the feature from the image encoder and get something that is good for language, right? And yeah, and in the second part, vision to language generative learning. Okay, the second part, is be able to generate text based on what we place inside that. So let's look at method. Oh yeah, damn, I remember this. See, yeah. Okay. Yeah, so basically the Q-former goal, this is gonna be a stream of consciousness. The Q-former's goal is to be able to take things from the image encoder and a text from the user, and then put them in the large language model to generate new stuff. So let's see. Method. We propose Blip2, a new visual language pre-training method that bootstraps from frozen pre-trained unimodular models, so one modality, in order to bridge the modality gap. We propose a query transformer Q-former pre-trained in two stages. Visual language representation learning stage with a frozen image encoder. Okay. And vision to language generative learning stage with a frozen. Okay, so the first part is to be able to represent vision and language, basically. So I have something from the image encoder. This is frozen, it's not trained, and I have some input text. And the second part is to be able to generate from these things. So, and if I remember correctly, yeah, they have three stages. The three stages. So again, the task is to get an image, you get a text, and you generate text, right? We get an image, we get a text, and this is generated. Okay. So the architecture is the following. So we have n blocks of this thing here is a self-attention. You put some queries are learned. You have cross-attention with a token from the image encoder, and then you just have a feed forward. You know, these two attention are shared. They are the same weight. On the right, we do self-attention on a text, and then we output something. And the way we use these outputs, you know, it's based on which stage are we. In the meantime, yeah, sorry, I've just seen that the demo is ready again, but we can have a look at that later. So let's see. We propose QFormer as a trainable module to bridge the gap between a frozen image encoder and a frozen LLM. It extracts a fixed number of output features from an image encoder independent of input image resolution. Okay, independent. Usually if that is a VAT, it's dependent, even if, I mean, if you don't use weird tricks. As shown in this figure 2, QFormer consists of two transformer submodules that share the same self-attention layer. Same self-attention layers. An image transformer can interact with the frozen image encoder from visual feature extraction. Yeah, an image transformer can interact with the frozen image encoder for the visual feature extraction. So it's this thing on the left. A text transformer can function as both a text encoder and text decoder. This thing here. We create a set of number of Laravel query embeddings as input to the image transformer. Okay. The queries interact with each. The queries interact with each other through self-attention. Yeah. So we do the self-attention and we interact with each other. Inserted every other transformer block. Okay. Inserted every other. Yeah. So we always use the same query on all this block. We always place the same query. The queries can additionally interact with the text through the same self-attention layer. Yeah, because if this is shared, I guess you concatenate this, right? And so each query can have a look at each embedded token from the text and vice versa, if you don't mask. Depending on the pre-training task, we apply different self-attention masks to control query text interaction. We initialize QFormer with the pre-trained weights of paired base. Interesting. Whereas the cross-attention layer random initialized. Yeah, because you don't have this. Okay. QFormer contains 188 million parameters. Note that the queries are considered as smaller parameters. Our experiment used 32 queries where each query has dimension of 764. Yeah, same as the dimension of QFormer, I guess same as the dimension of part. Used Z to denote the output query representation. 32 queries of 768 parameters each. The size of is much smaller than the size of the frozen image feature. So this is, guess, it's VAT large, yeah. This bottleneck architecture works together with our pretraining objective to force in the queries to extract visual information that is most relevant to the test. Yeah, because like you have less queries, you have a lot of stuff, so I guess you need to decide which one you want to attend on. So the first stage is bootstrap visual language representation learning from a frozen image encoder. In the representation learning stage, so we want to represent images in text, I guess. We connect QFormer to the frozen image encoder and perform pre-training using image text pair. Yeah. So we want to connect images and text. How do we do so? We aim to train the QFormer such that the queries can learn to extract visual representation that is most informative of the text. Inspired by Blip, we join optimized free pre-training objective share the same input format and model parameters. Each of that you apply a different attention masking strategy between queries and text to control their interaction. So we start with the image text contrastive learning, etc. Learns to align image representation and text representation such that their mutual information is maximized. This come on English. So by contrasting the image text similarity of a positive pair against those of negative pairs, contrasting the image text similarity. So we check the image. I guess the image text similarities. I guess whatever it comes out from here, whatever it comes out for here, we know that they are on the same pair, so they're positive pairs. We check that they are close to each other. We line the output query representation Z from the image transformer with the text representation T from the text transformer. So Z is here and T is here, and we align them. Where T is the output embedding of the class token. Perfect. Since Z contains multiple output embeddings and one from each query, we first compute the pairwise similarity between each query and output T. So here we have all this query here, right? We do the pairwise similarity with the class token. Then I guess we took the highest one and decided the highest one as the image text similarity. To avoid information leak, we employ a uni-model self-attention mask. Okay. So this is how we mask. On the first stage, the uni model. So this means so gray means it's mask, white is not mask. So Q, I guess you need to write it this way. So Q can see Q, right? I can do Q and Q. They can see each other. I cannot do Q and text. I cannot do text and Q, but I can do text and text, right? So Q can only see the other Q, and text can only see the other text. In this way, we do not mix information between queries and text, right? So the queries can only basically see each other in the self-attention and see the image, the feature from the image. The text can only see the text embeddings, and that's it. And then basically you want to make sure that these features are aligned because they represent the same thing. Like if we have an image of a cat that is wearing sunglasses, we want to make sure that the features are aligned correctly, right? And you force the image transformer to be able. So the only thing that this thing can do is extract meaningful feature from the image embedder, right? So you start by doing this, and then what you want to do is the image random text generation trains the Q-format to generate text given input images as the condition. Since the architecture of Q-format does not allow direct interaction between the frozen image encoder and the text tokens, because this cannot flow directly here. I mean, even if TTs can attend to each other, they cannot see the image encoder features. The information required for generating the text must be first extracted by the queries and then passed to the text token via self-attention layers. Therefore, the queries are forced to extract visual features that capture all the information about text. To employ a multimodal causal self-attention mask to control query text interaction, similar to the ones used in UniLM, the queries can attend to each other, but not to the text token. Each text token can attend to all the queries and its previous text token. Okay, so if we want to force this thing, basically to only look at the image encoder to generate text here. Okay, so we want to force the queries to extract meaningful information. It means that from the text transformer, we can look at the text, right? And we can look at the queries from the query's point of view, we cannot look at the text. But since the queries can look at the image encoder, in order to generate text, we will use the queries that use the image encoder. So the queries will have to extract meaning from feature. If we look at the mask here, queries, cannot see text. Text can see text and can see, you know, the text that is generated up to that point, I guess, right? So this will become a generative transformer. And yeah, then you do image text matching, aims to learn fine grade. Yeah, because now we want to have the fine grade features, alignment between image and text representation. It is a binary classification task where the model is asked to predict whether an image text pair is positive, match, or negative and match. Use a bidirectional sample attention mask where all queries and text can attend to each other. The output query embedding Z thus capture multimodal information. We feed each output query embedding into a two class. Okay. Classifiers, the logic. Okay. And average all queries, the average all logic across the query. Okay. So basically, then as the last step, queries can see each other, can see the text can see all the text, can see the queries, and then the queries can also see the image. And you place an image that here is an image of a cat wearing sunglasses, and you have some labels like you have 1 if it's a positive match, so this text is correct for this image, or 0 if this is not correct. So if here I would have the sentence a dog wearing sunglasses, that will be a 0, right? Because it will be incorrect. And then we do the last tuning, the last training in this way. And by doing so, the queries can also look at the text. So now the queries can also capture multimodal information, I say. So the whole goal here is that at the end of this thing, you should be able to have a plug and play module that you place between an image encoder, in this case, I guess has to be a VIT, and a frozen image encoder, frozen language model. And this thing can basically look at the image, can look at the text, and can generate meaningful feature from them that you can pass the language model. But this part was just the fine tuning. And then how do we actually use it with a frozen large language model to generate things? So I guess yeah, bootstrapping vision to language generative learning from a frozen large language model. So in the generative pre-training stage, we connect QFormer, the frozen image encoder touch, to a frozen LLM to harvest the LLM's generative language capability. As shown in figure 3, we use a fully connected FC layer to linearly project the output queries embeddings Z into the same dimension as the text embedding. Okay. The projected queries embeddings are then prepared to an input text embeddings. They function as a soft visual prompts that condition the LLM on visual presentation extracted by the QFormer. Okay, they function as a soft visual prompts. Yeah, so something about the image. That condition. Okay, so basically you drop the whole thing here, except that it is shared. So this thing on the right was just a way to learn meaningful queries that can look at themselves, can use the image encoder, and are able to capture multimodal information. So you place the queries here, right? And bootstrapping from the decoder base large language model. This is a decoder based large language model, like I guess Llama, right? And so yeah, you have your image encoder, QFormer, you project down to the right dimension here, and then you can just start generating. Right? Yeah. Right? um, a decoder based on an encoder, decoder based on an decoder for decoder based. We portray with the language modeling loss. We portray with a frozen range starts to generate text condition on the visual representation for encoder. We pre-train with the prefix. We pre-train with the prefix language model logs where we split text to two parts. Okay. Okay. So what QQ format does is be able to use a frozen image encoder and get the right information from the image and translate that from a frozen language model, right? And you could say, hey, but why do I have to do this thing in the middle? I can just take this and train just a fully connected part, right? And place it here. I guess that you can do that. The issue is that, first of all, the number of queries that you get from here are smaller than the number of tokens that you get from the image encoders. So I guess they were showing 257 and now you get 32. So this is some good sort of way to train something that is able to get very good it's able to very good get what you need to know about the image, you know, to pass to the large language model. So let's go back to demo. Actually, let's go back to the demo. So here I asked the model, you know, because the model said that this was a sword, and then it said that it's a stick or a branch. And I say, yeah, it's not really correct. Can you make 10 guesses about what the object is? Sure, here there are 10 guesses about what the object in the image might be. Broom, baseball bat, a hockey stick, a tree branch, a pool cue, a golf bag, a ten. Nope, it was a guitar. Okay. So yeah, so now we know what the Q former is. So I guess what they did is they just took this architecture, place Vicuna here, and trained this, right? So let's go back to the paper. Yeah, so let's see the method. MiniGPT-4 aims to align visual information from a pre-trained visual encoder with an advanced large language model. Specifically, we utilize Vicuna as our language model, which is constructible Llama and can perform wide task linguistic. Yeah, we employ the same visual encoder using Bridge2, which will couple with the pre-trained Q former, but both language and visual models are open source. We target to bridge the gap. Yeah, we had that before. To achieve an effective MiniGPT-4, we propose a two-stage training approach. The initial stage involves pre-training the model on a large collection of aligned image-text pair to acquire vision, language knowledge. I don't understand. So they are not. Yeah. So this is pre-trained. So what do you need to train? Just a linear layer. Why are not? Why they can? Why they didn't just pre-train as they did in the Blip2 paper? I guess they say that before, right? If you just pre-train in that way, it's not really working well, I guess. We should try the Blip2 paper. Do they have a demo online? Blip2 demo. Yeah, they have it. Okay. So yeah, yeah. Image. I want to. Can I add an image? Okay. Caption out. Okay. what would an Italian what would Italians say if you put pineapple on whatever food is on it? So then it needs to know that that's a pizza. In the meantime, I'm gonna put some water. Do you think it's going to work? Okay, we are gonna check that later. Okay, sorry, wrong paper. Okay, so during the initial pre-train stage, a model is designed to acquire visual language knowledge from a large collection of aligned image text pairs. We regard the output from the jet projection layer as a soft prompt. Yeah. So the same thing as we just seen in the Blip2 model. So this is a soft prompt. Now I guess we want to fine tune in a way that is, I guess, instruction based, right? And yeah, through the entire pre-train process, both the pre-train visual encoder and the train frozen, all the projection being trained. Okay. Our model undergoes 20,000 train steps with a batch size of 256, cover approximately 5 million image text pairs. The entire process took about 10 hours to complete 2 days. Yeah. Issue of the first pre-train stage. Okay, following the first pre-train stage, our MiniGPT-4 demonstrated the capability to possess a wealth of knowledge and offer reasonable responses to human inquiries. However, we observe essentially where they struggle to produce coherently within outputs, such as generating repetitive words, or sentences, fragmented sentences, or irrelevant content. This is should hinder MiniGPT-4 ability to engage in a fluent visual conversation with humans. We also have noticed a similar issue we're also facing in GPT-3, despite being pre-trained on an extensive language dataset. GPT-3 could not directly generate language outputs that are in accordance with the user intention. Through a process of instruction fine-tuning reinforcement learning for human feedback, GPT-3 3.5, we can discover to produce more human-friendly outputs. This phenomenon bears a sample of the current state of MiniGPT-4. Following its initial pre-training stage, as such, it's not surprised that our model may struggle to generate a fluid, natural human language output at this stage. And then, so this is like, first, you train on a bunch of stuff that is more or less good to make it understand it more or less, like the right alignment. And then you go ahead and bang, you fine tune it, right? And yeah, by the way, there was an error in the demo. Yeah, so creating a high quality alignment dataset for visual language domain towards achieve greater naturalness in the generated language and enhance the model usability. A second stage alignment process is essential. While in the realm of NLP, structured fine-tuning dataset and conversation are easily accessible, no equivalent dataset exists for the visual language domain. To address this deficiency, we carefully curate a high-quality image text dataset specifically tailored for alignment purposes. This dataset is subsequently, I'm butchering it, utilized to fine-tune our MiniGPT-4 during the second stage alignment process. Okay. This is so exciting, this is really so fucking cool. Initial alignment image text generation. In the initial phase, we employ the model to derive from the first pre-training stage we employ the model to learn from the first protein stage to generate a comprehensive description of a given image. So here we want to do a capturing basically. To enable our model to produce the more detailed image description, we have designed a prompt that adheres to the conversation framework of the Vicura language model as before. Human, image feature, describe this image in detail, please give as many details as possible, say everything you see. Assistant. In this prompt, image features represents the visual feature produced by the linear projector layer. I would like curious, like in the code, how then you translate from this prompt to the actually tokens, like use cities, and you know that you need to prepend to place there. Yeah, I guess that's the way. To identify incomplete sentences, we examine whether the generated sentence exceed 80 token. Cheap and smart. If it does not, we incorporate an additional prompt, human continue assistant, prompting our MiniGPT-4 to extend the generation. By concatenating the output from both steps, we can create a more compressed image description. Okay, so they use their model to create a better caption of the image. This approach enables to generate more image text pair with detailed informative image description. We understand 5,000 images from the, okay. You know, this is something cool, like, you see that your model is doing something that you don't want. You prompt in a smart way. If it's not working, you insist, and then you collect the new data from that, and then you fine tune it again. Yeah, from there, employ this to generate corresponding language description for each image. Data post-processing. The generated image description still have much noise and contains the errors, such as repetition of words or sentences and the presence of incorrect statements. So here, really, I'm thinking, okay, if I am one of these people who implement that and say, oh, the temptation will just dump my old dataset on GPT-4 and say to fix it, it's so big. In order to mitigate this issue, we employ ChatGPT. Fuck. Oh. So are deaf. Ooh. I mean, I just say that, you know, imagine the temptation of just taking your data set that is still not correct and dumping to GPT-4, ChatGPT. I mean, they could have used GPT-4 at this point, right? I mean, would it be so big? They did. So it's no commercial. Damn. Yeah, fix the error in the given paragraph, remove and repeat the sentences, meaningless character, non-English sentence, and so on, remove unnecessary repetition, rewrite any incomplete sentences. Okay, upon completing the post-processing stage, we manually verify the correctness, and okay, and then we take, yeah, 3,500 out of 1,500. It must just be satisfied the requirement. During the second stage, we fine-tune our protein model with the curated high-quality image text. Pairs, during the fine-tuning, we use the predefined prompt in the following template. Image feature, image instruction, okay, assistant. This prompt represents randomly sample instruction from a predefined instruction set containing various forms of instructions such as describe the image in detail, will you describe the content of the image for me, blah blah blah. It's important to note that we do not calculate the regression loss for this specific text image prompt. I don't know what they mean with regression loss, but that's okay. As a result, MiniGPT-4, I mean, what does it mean regression loss in this case? I'm not a text expert, so I'm gonna do what I do best. So that is data. So what is regression loss and what is in this context? I mean, it's so cool. GPT-4 is you can just prompt it with some random text. Yeah, okay, we know that. Then, particular is a regression problem where they don't. Yeah. And what do they calculate it? No idea. So let's go back to that. Nope, nope. There we go. As a result, MiniGPT-4 is not capable of producing more natural, reliable responses. Furthermore, we have observed that the model's fine-tuning process is remarkably efficient. We don't require, I mean, kudos to these people. GG, well done. But you're using ChatGPT, come on. But I mean, it makes sense. It makes sense because Vicuna is using ChatGPT, but at the same time, damn, could be. I mean, it could be so cool. Yeah, I mean, like you need to invest the time to fix that. But if it's 3,001 and 500, I mean, no. Damn, yeah, I wonder if one can just train a simple model to fix the repetition. No, it cannot be so simple, yeah. Well, furthermore, we have observed that the model's fine-tuning process is remarkably efficient, only requires some 403 steps. With the best set of time, we take about 7 minutes with on a single 100. Yeah, nice. And yeah. Well, GG, GG, GG. Now we need to wait for somebody to train GPT-4 all or the Dolly 2, make a data set, you know, fixed with their stuff, and yeah, but they haven't, damn, they haven't released the old data set. They just have this weird thing. I'm gonna go on GitHub and ask data set. I have a folder here. Here we go. These are all MIT data sets, if I'm not mistaken. GG, GG, GG. So let's have a look at the data from the alignment. Nope. Visual Studio Code. Here we go. Here we go. Bigger. So we have image folder and this thing. So let's see the caption here. So the caption, wrap, come on. So the caption, this is image 2. The image shows a man fishing on a low next to a river with a bridge in the background. Trees can be seen on and the sky is cloudy. Okay. So let's try to look for some random shit here. Earning per share, 110. I mean, you know, I don't really know what I mean with cool rated. Oh, I just 100. Okay. This is an image of a group of investors watching a number on screen. They appear to be interesting and focus on the information we present. The image is in black and white with investor. What? Image D 110. 110. Am I missing something here? So let's go, oh boy, so let's go back to step, okay. This image shows a kitchen. I'm gonna put this here and make this bigger, nice, and what? This image shows a kitchen with stainless steel appliances, blah blah blah. And so if I go 4, I mean, I can put it here, so yeah. Yeah. I mean, it's wrong. The image shows a group of people walking down a sidewalk, all these assigned as right. Get scientific right. Get seismic right. Well, I should make a PR, guys. So let's make a PR. So let's make a PR. Oh no, wait. I mean, I was thinking that they actually have the data there. Get scientific right. So if I look for red, okay, image 32. Yellow shirt bro is holding a trophy in his left hand. There is a red carpet. No, no, there's something wrong. There is something wrong with this dataset. There is a red carpet on the ground in front of him. Behind him there is a wall with a banner that reads Indian. He's holding a trophy. No. So no. There is something wrong here. I need to make a PR. I need to make a PR. Copy. I mean, I need to open an issue. Where descriptions in the dataset. Hi there. Thank you for the amazing project. I was looking at the dataset and I found some instances in which the text description is heavily hallucinated. For instance, take image with image ID equal 52. No. I need to copy. It's not copying. Should I continue further? The description says I mean it's not, I don't know if it's joyful. So all this thing all the bold text is not something that we can see from the image. What is going on here? Sweet. A smile. Am I missing something? Thanks a lot. Purple. Yeah. Yeah, I mean, of course it's this describe. So in this issue, so sometimes his model may describe image with imagination. If this is the data, yeah, image D for 52. I skipping every two of them. Say 557. Pew. Yeah, I should have opened them with the terminal. Okay. There is no water in the there is no fountain. Well, oh yeah, I'm sorry. So here, image 557, no fountain. It says with a stone fountain in the center. So yeah, I mean, I don't know. Oh boy, I'm gonna keep you posted on the issue on GitHub, and yeah, I think we will see in the next one. Bye, ciao.